Photographers are often forced to take images through obstructing elements. In this work, we present a method to automatically remove these obstructions from a short sequence of input images. For instance, when taking images through a glass window, reflections from indoor objects often obstruct the outdoor scene we wish to capture. Our algorithm automatically decomposes the sequence of images into a background and reflection component to produce a new, clean image where the reflection has been removed. Similarly, when photographing a scene through a fence, we would like to remove the occluding fence from our image. Again, our algorithm is able to decompose the sequence into the background and occluding image to produce the desired defenced image. We now describe our algorithm and demonstrate each step on the decomposition of 5 images containing reflection. It is challenging to directly analyze motion on pixels. Instead, we start from the motion of edges, which is less affected by the mixture of the 2 layers. We begin by performing candy edge detection on the frames to extract the edges from each image. We then match edges in each of the frames to a reference frame, the middle frame in the image sequence. Here we show the flow field for each of the frames in the sequence. Using Ransack, we then discover the first and second major components of the edge flows. These flow components correspond to the motion of the background and reflection, respectively. We then interpolate dense flow fields from sparse edge flows for both the background and reflection motion. Here we show the interpolated dense flow fields for each frame. Warping each of the images to the reference image using the initialized dense flow fields produces 2 images per frame, corresponding to the background and reflected flow. This results in a series of images where the background component is nearly static, and another series where the reflected component is nearly static. The initial separation of the background and reflection is obtained by projecting each image to the reference frame using the 2 motion fields and combining the projected images. Using this initialization, we minimize the objective function by iteratively solving for the images and flow fields for background and reflection layers in a coarse-defined manner. The coarse layer helps us to correct low spatial frequency errors before refining each image. Here we show a sample of results. First, the user takes a short video using a smartphone. Then, 5 to 7 frames are sampled from the video and are used as input to our algorithm. Using these frames, we are able to recover the background of an image with the reflection removed. We are also able to recover an image of the obstructor, in this case, the reflected image. We show a couple other examples of reflectance removal. Here is an example of a challenging night scene. Notice that although the reflectance image was not clear in the original images, by decomposing the images in this manner, we can get a clear picture of the indoor scene that was being reflected in the original image. Here we show an example of a sign with text that is being occluded with reflection. Some of the words, such as students, are difficult to recognize. However, by using our algorithm to remove the reflection from the sign, we produce an image that is easily readable. Once again, we are also able to recover the reflected image that was previously hard to make out. In this example, we are trying to remove the reflection of a textureless slanted plane. Due to the lack of texture, this example is especially hard. However, our algorithm is still able to handle this example fairly well and cleanly separate the background and reflection. Here we show some examples of our algorithm removing an obstructor. In these cases, we also simultaneously estimate a background obstructor alpha mat. In this case, we are able to remove raindrops from a window. In this case, the obstructor is transparent, so the alpha mat is not binary. Here we show another example that requires a non-binary alpha mat. In this case, we would like to remove the distracting fence in a video taken of a tiger at the zoo. One application of our algorithm is to remove the reflections from a series of panorama images. Directly stitching together these images produces unwanted artifacts due to reflections. However, our algorithm is easily able to automatically remove this reflection to produce clean images that can then be stitched together.